All right, let us get started on our lecture 27. In this lecture, we're going to focus on the cash flows, different type of cash flows, including single cash flow, uniform cash flow, geometric cash flows, general cash flows, all this type of cash flows. There's a lot of variety here for sure, but really they are all basically apply what we learned from last class, which is just how to use a present value and convert that to future value, or how to convert the future value to present value, right? The general concept and calculation we already learned. We just apply that to different cash flows. As long as you understand the concept with no problem, have that totally understand, you should have no problem here. So really, here's one example, right? We want to find the equivalence with multiple cash flows. Let's say we want to calculate, we want to compare different cash flows. And one example would be, this kind of example, right? The loan at the beginning of year one, we got $1,000 loan, right? And then we're going to have that for 3 years. There are two repayment options, and the interest rate is 10%, right? So with all this information, we want to understand which one is better, really which one is better, right? And then that's basically what we want to figure out, how do we use equivalent calculations to convert multiple cash flows to a single cash flow? Then we can basically compare, right? Because look at these two options. One is that at the beginning of year one, right, we borrowed $1,000, and then at the end of year one, we pay back $100. At the end of year two, we pay back another $100. And then at the end of year three, we pay back $1,100. Right? That's option one. Then there's a different option. This option is at the end of year one, pay nothing. Same at the end of year two, we pay nothing. But at the end of year three, we're going to pay back $1,331. We pay back that much money, right? So which one's better? Again, we want to answer that question. We need to compare that at the same. We need to do the equivalence calculation and compare them at one cash flow. Because, okay, year one, you need to pay more. Year two, you need to pay more. Year three, we are paying less, right? Which one is better? It's really hard to say. Okay, if we can't look at here, year one and year two, we are paying $200. But year three, here, compare option one, option two, two, actually we pay $231 more, right? So are they really equal? 231 sounds like, bigger than 200, but they are at a different year. How do we know it's really big or not, right? So that's basically what we need to do. And so we're going to talk about the cash flows. Then later on, let's come back and see which one is really a better choice, right? So here are two different kinds of cash flows. Some are easy to address, some are harder. Either one, let's say a single one is the easiest one, right? We're going to talk about this one first. So basically, for a single cash flow, we only have one cash flow. It's either going in or going out, but there's only one. All right. So something like this, that's one single cash flow, right? Either we have one present value, we need to find out the future value, or we have a future value, we try to find out the present value, right? Sometime in some rare cases, we might need to convert this to a year in the middle, maybe year two or year five, but it's always the same, right? So here the annotation you already know. F means future sum or future value. P is present value. I is interest rate. And N is time periods. And if we want to find out the future value, basically it equals to P multiplied by 1 plus I powered by N that give us the future value, right? Future value should always be bigger than present value. If you did all the calculation and then you find out, okay, future value is actually lower than present value, there's something wrong, right? In Excel, we can use the future value function as well. So we'll show that. I'll show that in a minute. Then if we convert this, we can also use future value to calculate present value. P equals to f y by 1 plus I powered by negative n, right? In this case, P will always be smaller than f. Don't change. Present value always smaller than future value. This arrow, if we convert this arrow to here, this should be shorter, this should be longer, right? The cash flow in the future should be longer. Same thing, we can use Excel to calculate this. So I'm going to show you, actually here's one example, right? So let's assume the present value is $2,000, the interest rate is 10%, and then the time period is 8, right? So what I can do is that I'm going to delete this. So I can use the future value function. There are multiple ways to do this. One thing is that you can just directly type equal FV, and then that's basically the future value function. And then you can see that it allows you to input rate, number of period, cash flow, present value, type, all those kind of things, right? So here we only need to worry about the information we get. It's basically present value, interest, and number of period, right? So that's what we're going to do. The rate is 0.1, that's the interest rate. Period, 8. PMT, we don't have that information, right? We do have the present value, so I basically add another comma. And the present value is $2,000, right? So we put this, that's all we want to find out. And the result is 4,287.18, right? You can directly calculate that. Of course, you can also use a function here. So in Excel, you can go to formula and click on this arrow next to financial, and you can go down to future value, right? So here it's the same thing basically, but you can put 0.1, 8 period, and the present value is 2,000, and did I do something wrong? It should be 0.1, not 1, right? 0.1, it should get you the exact same result, 4,287.18, right? That's the dollar amount. So that's how to calculate the future value, use the Excel. Same thing for present value, right? So what you can do is that let's say you want to find a present value, you can just put PV, and then there's the present value function, right? Rate is 0.1, the same. Number of period, 8. Don't have PMT, so add another comma here. And then the future value, which is, we know from above, is 4,287.18, right? And that gives you $2,000, right? So the present value is actually 2,000. And the way you do this is the same. You can go, you can come here and find out the present value function here, PV, and you can put the same information to get the result, right? Give you $2,000. It's the same thing. So pretty handy, very handy to use this. One thing I don't know if you notice is that, so look at this. We put 0.18, $2,000. All these are positive, right? But the result it gives is actually negative. The result it gives is actually negative. And then in here, you can actually see that there are brackets around this number. Also shows this is actually negative. So what it means is basically Excel is trying to give you make sure your number, the total value equals to 0. Total value equals to 0. So if you use this number and calculate all this result, this actually means at the end, you're going to have 4,287.18, and the negative cash flow to bring it to 0 will be negative 4,287.18, right? That's why this is like this. So, I mean, don't be alarmed and thinking this is wrong, but basically whatever number you get, you need to take the opposite of the value, right? So those are based on present value, we calculate future value, or future value to calculate present value. It's also possible that what we have is future value and present value, and we don't know rate. We try to find out interest rate, right? It could be possible. And of course, using our function is pretty straightforward, right? We can move p to the other side and then take the root of n, then minus 1. That will give us I. A little bit detour, but we can still easily find that number. We can also use Excel to calculate this. And I'll show you right here. This equals to, again, you can just type rate, and then the period will be 8, right? PMT, we don't have that, so another comma. PV equals to 2000, you can write that. And the future value equals to 4287.18. And if I hit enter, you'll notice that this actually cannot give you any number, because what you have is that 2000 and 4000 are all positive, right? Remember what we said, we want to bring it to 0. So you actually need to change one of this to negative. So if you add a negative sign in front of 2000, that gives you 10%, right? So basically it says the interest rate is 10%, which is exactly what we have before. Similarly, you can obviously click here and go to the rate function and input those numbers here. It's the same thing. I'm not going to do that again. Generally speaking, really calculating the single period formula is pretty straightforward. It's much easier. Another function we are going to use is actually the MPER, right? So find out the number of period. This one is actually a bit tricky to use our hand to calculate. So it's a good idea to just use the Excel. So Excel is the same thing. What we have is we can use the MPER function. So this equals to MPER, number of period. Then the rate is 0.1, still 2 comma, present value negative 2000, future value 4287.18, and this gives us 8. The period is 8, right? Of course, we just take the rounded to the integer here, right? It's 8. So that's the first type, right? The single cash flow, relatively easy, pretty straightforward to calculate. The next one is a uniform or equal payment cash flow, payment cash flow, right? Something like this. At each period, it's a little more complicated because at each period, you have some cash flow going in or going out. It's always the same. That's why we call it uniform, right? At each point is always same and they are equal payment. So in this case, this could be the way to calculate what will be asked, right? Especially for this class, what's going to be asked. Given n time periods, uniform interest payment is A, meaning that at each time period, year 1, year 2, year 3, or month 1, month 2, month 3, the payment is always A. Interest rate per time period is I, and then we find the future value, right? Could be the same information, we need to find out present value. Could be we have P, we have N, we have I, we need to find A. Or we have F, N, I to find A. All these are often ask you to find, and mostly you're going to see this kind of problems in our class. It's not that easy to solve for n or I. It's not that easy to solve for n or I. That's trickier. But these are the function. You can directly use them to calculate. And as here you can see, this is, you can mathematically prove why these functions look something like this. But really, as long as you have this function, you have this formula sheet, you can, and if I give you A, I give you F divided by A. Yeah, I give you interest rate, I give you N, and then you can, based on A, what will be the future value basically, then you can easily calculate all this number here, right? Same thing if we have A, how do we calculate P? We have P, how to calculate A, we have F, how to calculate A, so on and so forth, right? So those are the, during our final exam, this will be given, and then you should have this information in front of you. So that's the type of problems, and we're going to see a few examples here. First one, future sum, right? And the question, so again, this is the uniform theory. You can see that at each time period, 1, 2, 3, 4, 5, the cash flow is the same, A, right? And then basically with A, with N, with I want to, we know all these three. How do we calculate P or F, right? How do we calculate P or F? So we can use Excel to calculate for sure, right? So in here, you can see that the question here is, for $3,000, if each time period, the number is $3,000, 10 time period, n period equals to 10, and the interest rate is 7, how do we find the present value, right? Which is A equals to here, PMT from Excel, right? So we can input that in here. We use the same function as we did before. This is for present value. No, this is for future value. Let's find the future value first. So rate is 0.7, period is 10, PMT this time we have, which is how much? $3,000. $3,000. And that's it, right? Oh, did I do something wrong? 10 period. Oh, the rate, I got this wrong again. This is 7%, not 70%, right? 7%, and this is the result, right? So you investigate, let's say, assume at time 1, time 2, time 3, time 4, time 5. Each of the time period, you investigate $3,000 into stock market or save them into bank. Then at the end of year 5, you will have $41,449.34, right? That's the final result. And so that's how to find the future value, right? Same thing we can find the present same thing we can find a present value, which basically PV equals to, the number is really the same, right? 0.07, 10 period. The PMT is 3000 again. And that's our result, right? So the present value is $21,070.74, right? So it's the same number here. That's how we calculate this two number, right? But remember these numbers. So 10-year period, the rate is 7%, and then cash flow is 3,000. Try this too, right? Okay, use your calculator. Try this too. If we input those numbers here, do we get the same result like what Excel calculated for us, right? Maybe take 2 minutes and try to calculate this two value. All right, I hope you calculate that. I'm sure you get the same result. So next, sometimes we have future value. We have I and we have N, right? The time period. How do we calculate A? So basically, what are the values here, right? What are the values at each time period? So same thing, we can do. We can use a function PMT that allow us to find A. The rate is 0.07, number of years, 10 years, present value 21,070.74, right? That's a number here, and you can see that A equals to 3,000, exactly what we inputted before, right? Same thing, if we don't have present value, but we have a future value, we can input that as well. The rate is 0.07, number of period 10, future value, present value, we don't have that, but we have future value. So 41,449.34. That gave us 3,000 again, right? So we can calculate the same thing. And pretty straightforward as well, right? But that's a different function, which is a PMT, right? And same here, right? We use Excel to calculate that. Can you maybe use this two function and try to see if you get the same number? Maybe take 2 minutes to calculate that. All right, so I hope you got the result. They should be the same, right? Now, calculate PME is pretty easy. Even use a function here, right? Calculate A is pretty easy. Now, if you want to calculate MPR or calculate rate, using formula is really hard. It's actually really hard to get the formula, and they can generate different results actually. So in that case, the best choice would be to use Excel, right? So Excel, you can use the exact same function we used before. One is rate, the other is MPER, the number of period, and input the right number there. Remember, if one is positive, you want to set the other as negative, so it's give you the right number. So in this case, you can calculate the result, right? I'm not going to show that here anymore. Pretty straightforward. Okay. So that's the uniform theory. That's a uniform series, right? I have a few examples here. Try this if you are interested and see if you get the same result. And all the functions are actually summarized here. All the functions are summarized here, right? Okay, with that, let's do one example and let's see if you get the right result or not. So here it is. The problem is from our homework 10, right? A local newspaper headline blared, Bo Smith signed for $30 million. So a reading of the article revealed that Bo Smith, the former record-breaking running back from Football University, signed a $30 million package with the Dallas Stars. The terms of the contract were $3 million signed bonus paid immediately. So immediately he gets $3 million, right? Starting at time 0. $2.4 million per year for the first 5 years. First payment will happen at the end of 1 year, right? And $3 million per year for the next 5 years. So our first payment will come at year 6. At year 6, right? If the interest rate is 8% per year, right? If the interest rate is 8% per year, let's do two things. One, calculate the cash flow, show the cash flow here. And two, find the present value of the contract. Find the present value of the contract. So let's do that. I hope you will try it there. Take 2 minutes first to show the cash flow, and then second, find the present value of the contract. Let's do the first one first. Maybe on a piece of paper, draw the cash flow and see what it looks like. All right, I hope you already tried it, and hopefully your cash flow looks like something like this, right? Immediately, Bo get $3 million right here. Gets $3 million right here, right? Then, then for 5 years, he will get $2.4 million per year, right? $2.4 million per year. So this is for the next 5 years, this is cash flow. A little bit lower, but something like this, right? And then for the year 6 to year 10, it's bumped up to $3 million, right? So something like this, That's another 5 years. So altogether, if you just calculate the pure number, they are all, they are basically like something like this, and you add them all together, that's $30 million, right? That's $30 million. But I mean, $30 million is across 30 years, right? But what we want to do is to find the present value of the contract. So based on this cash flow, take a few minutes and see if you can calculate this, the real cash flow, the real present value here. All right, I hope you have spent some time to calculate this. So, well, if we look at this cash flow, right, this basically has 3 parts. We want to calculate present value. So all these lines, we need to move back to year 0. Obviously, you can move one by one. Right? Year 1 convert to year 0. Year 2 convert to year 0. Year 3 convert to year 0. So on and so forth. But I mean, you can do that. But that's a bit time consuming. If we look at this, it has three parts, right? The first $3 million at the beginning of the contract. Then for 5 years, we have one uniform cash flow, and the amount is 2.4. Then for the last 5 years, we have another uniform cash flow, and for each year it's $3 million, right? So we break that into three parts, and we can convert each part back to the present value at year 0, right? First, we do this. Year 0, the first part. So basically here, right? We don't need to do anything here because this cash flow happened at year 0, right? So we don't need to do any conversion or anything. We already can calculate. Well, we just can put a number here. P0 equals to 3. P0 equals to 3, right? That's the first part. The second part is from year 1 to year 5. Year 1 to year 5. For year 1 to year 5, what we have is A, right? For each year, we have $2.4 million. We know period, which is 5 years. We know the interest rate, which is 8%, right? And I already have this function listed here. We know A, we know I, we know N. We're trying to calculate P. So P equals to A multiplied by, well, this big chunk basically, right? You can put the number here. That's exactly what I did, and calculate the total value. So if we convert all this part, not just year 1 or year 2 or year 3, all this 5 years, and we bring it back to year 0, the number we get is basically $9.58 million. $9.58 million, right? That's what we get. Remember, when you do this, when you use this, you bring it backward 1 year. So if you do this for year 1 to year 5, you bring it back to year 0. If you do this for if there's something, right, some cash flow start from year 2 to year 5 or year 2 to year 6, you can use the exact same thing, but it doesn't bring you back to year 0. It bring you to year 1. One single value, you convert everything into one single value, one single cash flow on year 1. You need to do one more time to bring it back to year 0, right? And we're going to see that example for the next part, the last part, which is from year 6 to year 10. For year 6 to year 10, right? This is we know A is here, right? A is here. We know A is $3 million. We know the time period, which is 5 years. We know the interest rate, which is 8%. And then we input this value here. Same thing, right? We know A, we know I, we know N. We want to find out P. We input all this value here. That gave us 11.93. 11.93, right? So this is the value. If we use this function here, we only got 11.93. But remember, when we do this, we bring it 1 year back. Bring it 1 year back, right? So meaning that we did this for a uniform cash flow from year 6 to year 10. When we do all the conversion, we bring it back to year 5 and get one cash flow. Year 5 for one cash flow. But year 5 is not present value yet. We have to bring it from year 5 to year 0, right? From year 5 to year 0. That's why we divided another 1 plus 0.08 part by 5, then to give us 8.15. That's this cash flow's present value at year 0. Okay, I'm going to explain that one more time. when we do all the conversion for a cash flow, let's say it starts from year n, right? Year n all the way to year n plus m, whatever that is. We bring it back to n minus 1. We bring it back to n minus 1. So n minus 1 may not be 0 yet, right? N minus 1 may not be 0 yet. So here, now what we did is that we convert all the future uniform cash flow to one single cash flow on year n minus 1. For 0 in year minus 1 becomes the future. It's still in the future, right? We need to bring that future value back to present value at year 0. That's why here we divided again 1 plus 0.08 powered by 5. That gives us the final present value for the third part of this uniform cash flow. There's nothing else left, so what we find is 3 part, we added that, right? Then we can basically add this together, right? 3 plus 9.58 plus 8.15. This is not 30 million. Yeah, it's still a lot of money, right? More than close to $20 million, but this is not really 30 million if we say that strictly from a present values perspective. All right, so that's how we do this example. I hope you understand how we did it. The third cash flow is a gradient cash flows. So basically, this cash flow is that the cash flow actually changes. You can see that at each time period, the value is different, but it changed by a constant amount each period. So you can see that it's basically follow a straight line here, right? Each period, let's say here we increase by $100, then compare period 2 to period 1. Then at period 3, also compared to period 2, we're going to increase $100 and so on and so forth, right? So end of period 1, maybe we have $0. Year 2, then it's become G, 3, 2G, and so on and so forth, right? So on and so forth. In this case, for a gradient cash flow, we actually have already have these functions to calculate. So what we have is that if we know G, so basically the increase from each period, and then we know I, the interest rate, and N, we can calculate. We can calculate these, right? And then we can also do the conversion to convert G to uniform cash flow, and that's how we do. We use this function to convert G to A, right? Same thing, we can use G with all this information to calculate F, right? We can calculate F, the future value. So that's how we do it. One thing I want to make sure you understand is that it always need to follow a gradient cash flow. Always need to have follow this pattern. What I mean is that at 0, it's need to be. Sorry, at the end of period 1, it need to be 0, right? At end of year 2, it's going to be G, so increase by a constant, and 2G increased by another constant. Year 4, 3G. But I mean, at year 1, like year 0, it's always need to be 0. No cash flow. Only in that case, then we can use this function, right? We can use this function to calculate present value. So here's the question. If it has to be 1, it has to be 0, right? We already said at period 1, it has to be 0. What if it doesn't happen at 0? So what if it's $100, $200, $300, $400, $500, $600? in that case, what do we do? Well, in that case, obviously, we cannot directly use this function anymore because, again, it's required to start at 0, right? In that case, we want to break our cash flow into 2 parts. So one is a uniform cash flow, which we always have a cash at, let's say, 100, right? So for each period, we take out $100 and make that a uniform cash flow. For the rest, if we use, before it's 100, right? Now we take out 100, now it's become 0, right? Then the future ones become, constant, adding a constant value. Then we have another gradient cash flow. Now we basically are converting 2 cash flow into the present value. One use the formula for uniform cash flow. The other one, we can use the formula for gradient cash flow to do the calculation. Right. So that's what we can do. So here's actually the example shows that, right? What we have is that here's our cash flow. At year 1, it's $2,000. Year 2, $3,000. Year 3, $4,000. Year 4, $5,000, right? And apparently, at the end of year 1, it's not 0. So we cannot directly use this formula, right? What we want to do is break this into 2 parts. So one part is annuity, and it's always $2,000, so it's become a constant or uniform cash flow, right? Then the other part is gradient cash flow. At the end of year 1, it's 0. Year 2, it's 1,000, so increase by 1,000. Year 3 is 2,000, increase by 1,000. Year 4 is 3,000, increase by 1,000 as well, right? So the increase is constant, right? Then, so in this case, for each year, the cash flow is $2,000. This part is $2,000, right? Plus, we know G, we know I, we know N. We can use this formula to convert this to an N, right? So we can convert this to an N. Now, after we convert this, obviously, so for each year, the A equals 2,000 plus this value give us $3,404, right? Then if we have A, well, now we know how to do it, right? We know how to find out the present value or the future value. Depends on what is needed, right? So that's gradient cash flow. The last one is interest rates vary over time. So this is actually interest rate over the present equivalent P of this type of cash flow occurring at the end of period N, Fn, with interest rate Ik in the case period, it's always change. It's always change, right? So in general, there's not a good way to do this. Only thing we can do is that we move cash flow 1 period at a time. Let's say at the end of the period, the future cash flow is $2,500. And then for 3 periods, the interest rates are different, right? So what we need to do is that use this, we first divide it by 1 plus 0.11. Then we can calculate, we can bring that to year 2, and then use year 2's interest to bring to year 1, and use year 1's interest to bring it to year 0. Do the calculation. So here's the calculation. You can see, right, exactly what we did, right? First period, second period, third period. We convert each one into find the value, and then multiply them all together. That's give us 1,896 at the beginning of the period. So the present value is this much, right? Okay, so that's what we get. Sometime in the engineering economy, you also hear the nominal and the effective interest rate. That is because in engineering projects and personal finance, the compounding period is often different, maybe less, most of the time less than 1 year. So to compare different cash flows with different compounding period, we definitely need to evaluate them on a common basis. So need to be either on nominal or on effective interest rate, right? Usually, annual rate is known as a nominal rate, right? A nominal rate of 12%. Compounding monthly means that the interest is 1%, which would be accrue each month, And the actual annual rate in this case is usually effectively greater than 12%. So the actual rate, which is the effective rate, is what we calculate the true annual compounding rates, right? That will represent the true interest earned or paid in a year. True interest earned or paid in a year. Okay, so not sure if you understand this, but here's one example. Let's say you borrowed something from the bank for $1,000, right? The bank told you the yearly interest rate is 12%, but it's actually compounded monthly. Right? If it's yearly and its rate is 12%, well, you can easily calculate at the end of 1 year how much money you own the bank, right? Basically, it's just going to be 1,000 multiplied by 1 plus 0.12, give you 1120, $1,120. That's how much you're going to own the bank, right? So at the end of year 1, you pay that much. However, if it's compounded monthly, not yearly, monthly, the rate will be totally different. Now, take 2 minutes and calculate this. See how much that will be, and see if basically what you are calculating is the effective rate, right? And see if that is higher or lower than what you get. Okay, I didn't put it here, but I hope you calculate the result, and I hope you find out that the result is definitely bigger than the total amount of money you own the bank is definitely bigger than $1,120, right? It's actually going to be 1,126.8 or $27. Where's the extra $7 come from, right? So basically what you calculate, instead of 1 plus 0.12, it's become 1 plus 0.01 and powered by 12. That rate is slightly higher than 12%. In this case, you actually need to pay a little bit more. right? So remember that nominal rate may be the rate what the bank tells you or the loaner tells you, but if they compound in different time period, the effective rate is usually higher than the nominal rate. That is guaranteed. Last one example, the credit company charges a rate of 1.375% per month on the unpaid balance at the end of the month. They claim that the annual interest rate is 12 multiplied by 1.375, which equals to 16.5%, right? That's their nominal. That's their nominal interest, right? That's what they're going to tell you. But try calculate this and see how much really it is. How much really it is. What is the effective rate? And we're going to talk this tomorrow during the class. Now, that's all I want to discuss today, and see you on Thursday.